Hello, everybody. Welcome to another short video where we learn a different concept that people want to learn from various classes that I teach. This time, we're going to look at correlational research, specifically when doing quantitative research. So correlations are one of my favorites. They are when you look at data and you have a whole bunch of dots like this and you can deduce some kind of pattern from them. You can see a relationship between variables. And it's highly useful, highly simple, I believe. And so the purpose of this video is to hopefully help you believe the same thing, that it'll be a threefold lesson. Lesson number one, first, as always, we got to figure out what the heck correlations are and how they ultimately help us understand our data that we have better. Two, we need to know how to interpret the correlations. You have the numbers. What do the numbers mean? Plus, minus signs. How do these relate to effect sizes of how good or strong the impact might be? We're going to look into that and then finally present you some warnings, things to be careful of when looking at correlational findings. And so just jumping right into things, let's look at what correlations are. So correlations are specifically a statistical number that help us measure how much two variables co-vary together. Right? A simple way to say that's how much they relate to one another, but as a friendly reminder, whenever we're looking at correlational research, we're looking at when one variable moves, X in this case, does the other variable move similarly? Do they move together? Does one go up, the other go down, the other one go down, and then that one goes up? Is what's happening with one variable causing or relating to what's happening with another variable. And so specifically, an idea of a couple variables we could talk about would be, maybe I'm curious how much a person plays video games, if that ultimately relates to how intelligent they are across the board, or maybe how good their grades are in a classroom. Either of those could be something we could see how much variable X relates to variable Y. That's one example. And so ultimately, let's say I went out and conducted hundreds of surveys and asked people this. And though this specifically isn't looking at gaming research and intelligence, just so anybody knows, this was actually on that title slide. But you get your hundreds of dots and you want to know if they're related to each other. Well, up front, before I even put the line I'm going to put on this on the next slide, notice how as one variable goes higher here, we go from left to right, the other variable down to up also seems to be getting higher, that these dots are moving in a pattern that kind of looks like this. That shows us that there's a relationship between these variables, a correlation to be specific. And so before we jump forward into interpreting that correlation and what it specifically means, first we got to get one more thing out of the way. A reminder, earlier in a different video, I talked about the different levels of data that a researcher needs to be careful of when they collect their data in the first place. This is one of those times where how you collected your data really matters, because correlation research, before we can even get into all this good stuff right here that we see, we have to make sure that we have interval or ratio level data. Okay, and so some examples of variables you might test if you've collected the data properly would be things like age and how fast you can run, how much soft drinks you drink and how much you weigh, how much sleep you get, and ultimately what kind of class grade percentage that you have. This last one here, color of laptop and class standing, is not something that you could test with correlational research, at least not if you categorized them based on like green, blue, yellow, pink, and class standing of either, I guess you could go tops and bottoms of the class, or freshman, sophomore, senior, junior. Those aren't quite the data you would need to be able to determine how, when one goes up, does the other go up or down? Because green versus pink versus blue, there is no up and down in that data. There's not one that's better or worse than the others. They're all just categories. And so in order to have correlational research, you do have to have interval and ratio level data to perform it. Now, assuming we've got that data, and now that hoping we know what correlations are, we can look a little bit more into how we interpret them once we get them from a program like SPSS. So Pearson is probably going to be the most common form of correlation that most of you will ever use or perform. And so without getting too much in the history, you can look up more about Pearson if you'd like. The R is the important thing we're going to remember with our correlation. When you use your programs, a lot of the times you're going to see this R, and it's a lowercase italicized R. Now, that R will always range from -1 to +1. Okay, there'll never be a -2, 3, 4, -6s, 7s. It will always be a number that goes between -1 and +1. And with that number, you can actually determine a few things. Number one, what the number is specifically tells us how strong the relationship is. So down here, I've got some different types of correlations, and I'll get into the positives and negatives in just a moment. But the intensity of the relationship is referring to how close together the dots are, or said a different way, when one variable is going up or down, is the other going up or down pretty consistently with the first variable. So you can see here that when this 0.9 goes to a 0.5, the dots are a lot more spread out. And when we get to a 0, meaning no correlation at all, notice how there is no pattern to the dots. They're just all over the place. People's responses, their values there is no pattern. But the farther we go toward a +1 or even a -1, notice how the dots get much closer together and much more predictable based off the values that are being put into the graphs. So our -1 to +1, what the number is specifically, tells us how intense the relationship is, how closely related those variables are. On the flip side, the positive or the negative sign tells us what direction the relationship is pursuing. So in the case of our positive correlations, anytime you have a positive correlation, it means that when one goes up, the other goes up, or if one goes down, the other goes down. Positive correlation means that whatever way, up or down, the first variable is behaving, the second one is behaving that exact same way. Okay, to be clear, and just so that people are not confused, a positive correlation doesn't mean that you just have all high value numbers as we get higher in the chart. And a negative correlation doesn't mean we're only dealing with negative numbers. The correlation tells you how the two variables are related. Do they do the same thing, or do they behave differently from one another? And so notice our positive correlation, when one goes up, the other's going up. It could also be that when this one's going down, the other one's going down. On the flip side, a negative correlation, when this one is going up, our second variable is going down. And the flip side would be, as this one's going up or down, this one might be going up. Okay, so the plus or minus sign, whether it's a positive or a negative one, or whatever value it might be, the plus or negative tells us the direction of the relationship, how the two variables are relating to each other. The number itself tells us how strong that relationship is. Now, in degrees of knowing how quote unquote good your R is, how much of an effect is being had between these two variables, the R itself is what we call an effect size. So if you have a 0.1, it's what we would usually regard as a small effect happening between these variables, a 0.3 being a medium, and a 0.5 or higher being a large effect. Now again, that would be a plus or minus 0.1, a plus or minus 0.3, a plus or minus 0.5. It doesn't matter about the positive or negativity of the number. It's the number itself that tells us how big the effect is. So an important note here before I move on, though you might have a 0.5 in your paper or in your study, or you might get a 0.1, be careful assuming that these little, easy effect sizes are the only way to interpret the numbers that you have. It's more important to go and look at the different research that other people have found, because, for instance, you might find a 0.3 in your study, but if everybody else has been finding 0.1s at most in their studies, that tells you that you might have done something or found something particularly large in your study. Even though it's a 0.3 by our current table here, 0.3 in comparison to only ever 0.1s from other people, tells us that this study's probably got something worth exploring more or looking into. So these are one way that you can interpret effect sizes of correlations. Another one, just a little pro tip, a little fun fact for you would be there's actually another effect size you can use known as R square, which simple, if we have a little r and you square it, it becomes big R, R squared. Don't get lost in the capitalization of it, but they do stand for different things. The little r tells us the effect size, the relationship between those two variables. The big R squared actually tells us something different. It tells us the percentage of variance that variables share with each other. In other words, variable X, right, are into how much somebody plays a video game. How much of how much someone plays a video game does it tell us impact I'm saying that awful. Let me try that again. How much of a person playing a video game impacts how intelligent they are? What percentage of intelligence can we deduce from the video game playing alone? Or vice versa, how much intelligence tells us how much or likelihood a person is playing a video game? So whereas the little r, we're looking at just how strongly they're related, the big R tells us based off all of the difference in dots that are happening in this exchange between these variables, how much of the differences that are occurring can we understand just based off this one other variable's relationship to our first variable. So I've done the math here just to show you if we had a R equals 0.5, which would be a large effect by little r standard. When you square that, it becomes 0.25. 0.25 doesn't help us as much. Let's times it by 100, which moves that dot over twice to make it a 25. 1/4 of all the variance that is happening in this intelligence versus video game hours relationship is being explained by just these two variables. That's a pretty good amount of variance. And so that is our effect sizes. That's how we interpret what R means. Now, the last thing, just briefly to go through, would be to be careful with some of the assumptions that scholars make when they work with correlational research. Because as I'm sure many of you have heard, you've probably heard the phrase correlations do not equal causation. And absolutely, that's something to always keep in mind. So I've got a little AI generated artwork here. There is a fair bit of data that suggests in the real world that the number of churches that a city has, the number of prostitutes that city has as well. The more churches you get in a city, the more prostitution you usually see in a city as well. Now, this is real data, real findings, which brings up a pretty interesting question. Is it, I guess we could wonder that the churches in a city are causing people to seek out prostitution? You go to your Sunday service and then you say, well, I need to get that out of my system. Or, I mean, maybe we could say that going through the prostitution, you go through that experience and you need to get it out of your system by going to church afterwards. The thing is, with correlational research, we don't know which one is causing the other. And some of you might be saying, God, I'm having a hard time even believing that these two things are related. Well, that is one of the first things I want to remind us, these pitfalls to be wary of. Because correlations do not equal causation, a better way to understand that, excuse me, is twofold. First, we never know what other variables might also be impacting the relationship between the variables we're currently looking at. So for instance, it is a high correlation between prostitution and churches in a city. They are highly related to one another, but a third variable that I don't discuss in that little statistic is that they're probably also both impacted by just generally the number of people that are in a city. When you have more people, you have more churches. When you have more people, you have more likelihood of prostitution. So it's very likely that prostitution and churches are not causing one another, but rather a third variable is leading to the effect that we're seeing. And so first and foremost, why correlations don't equal causation is other variables are likely at play that help us understand the relationship much better. We can't just assume because variables are related that one is causing the other. Okay, and said another way, even though it sounds similar, there's a difference here. number one is about recognizing other variables are at play. Number two is even if there is causation, even if, which we can't assume with our numbers alone, but even if there is causation, the way the statistic is calculated, the R, we don't and can't assume that we know which direction is causing the other. Okay, it might theoretically make sense to assume that one would be leading to the other, but mathematically, statistically, we don't actually get that assumption from the data. And so, going back to the original example of my video game playing and intelligence, maybe they are highly correlated, but is it that playing more video games makes you more intelligent? Or is it that being more intelligent means you're more likely to play video games? With the R alone, we would never know which actually causes the other. And you can see where you could get yourself into a lot of trouble with assuming we know which direction the arrow's going. The numbers don't tell us that. And again, theory might help us make such claims, but numbers alone, we can't make such assumptions. And so putting all that together, just some brief reminders to end off this video. Correlations are an interesting test statistic that allow us to measure how much two variables relate to each other, specifically how much they co-vary. The values that we get for these numbers, this R, is always going to be between -1 and +1. And those numbers help us understand two things. One, which direction the relationship between the variables is going, and two, how strong or intense the relationship is. Finally, there are things to worry about, that this is only ever a math number, a statistics number. We can't assume because we have a number that it fully tells us exactly why the number is what it is. Correlations do not equal causation, and we can't ever assume that the data we have tells us why the variables are related. We can only assume or now know that they are. So I hope this has ultimately helped clarify a few things with correlations. And I look forward to hopefully seeing you again in the next video.